All right, these are the dropped projectile slides. So, drop projectiles is going to be a part of kinematics, which just studies the just studies motion without the cause of the motion, and it looks at the four conditions of a moving object: time, position, velocity, and acceleration. So, these are the kinematic problems that we've been, or the kinematic equations that we've been using. Now, these are the drop projectile equations. Now, these are going to look exactly the same, and that's because they are the exact same problems. The only difference is that if you look, notice when I switch back and forth, well, kinematic equations, we've just used the x-plane for all the problems. Just assume that, yep, it's straight across, left, right, horizontal. But now we're going to be talking about drop projectiles, the up and like a just down motion. So now we're going to be working with the y-plane. And you can see this over here. As this person's dropping out, you can see that it's just like an up and down motion. Just for a drop projectile, well, that means that it's just going down. So we're just going to use the y plane here. So notice the origin is the starting position of the object. So what that means is that, well, at time zero, like we just put wherever it starts, that's where the origin is. Now this is just a personal preference. The math will work out no matter where you put the origin. Like you can put it where the object lands. Yeah, the math will still work out, but I just think it's easier if you put the origin where it starts, where the object originated. Now, everything's going to be on the y-axis for a drop projectile. So let's look at what this means for the variables. So v0y, that's the initial velocity the instant the object is dropped. Now, unless the object is thrown down, the initial velocity is going to be zero. The instant you let go of an object, it's at rest. An instant later, it's moving down. Now, after the initial velocity, after that instant, as it's moving down, the velocity is negative, right? And the final velocity at the end of the time interval, it's going to be negative. All the velocities moving downward will be negative because it's moving in a downward direction. Velocity is a vector, it has a direction. So AY, that's the acceleration of the object as it's falling. And as we've learned with Newton's second law, the ratio of net force to mass for all objects falling, like if we ignore air resistance, which we are for these problems, is going to be the same. And in fact, that ratio is technically negative 9.81 meters per second squared. But just to make the math easier, we're going to use negative 10 meters per second squared as it's highlighted there. Now, delta t, that's just the time interval of the falling object. Now, delta y is the final position, which will be a negative number, minus the initial position, the origin. Delta y will be a negative number. And the reason why it's negative is because the final position is going to be below the initial position. That's why delta y is negative. So you have the delta y, that displacement is negative. You have the velocity, and then you have the acceleration are all going to be negative, right? The only thing that's not going to be negative is that initial velocity, which will be zero. So let's look at how we solve a drop projectile problem. So just ask yourself the three questions. Which variable are you being asked to find? What three variables do you already know? Which equations has those four variables? So let's look at three different kinds of problems that we can have for drop projectiles. So this is a known height. An object is dropped and falls down for a displacement of negative 20 meters. What is the time interval of this fall? With what velocity does it hit the ground? All right, so let's ask ourselves, what is the first thing this question is asking us to find? Well, it's asking us to find the time interval. Now, notice the displacement is a negative 20 because, well, it's falling down. The final spot is going to be below where it originated. So it's going to be a negative displacement. So the first thing it's asking us for the time. Now, we know three variables. Now, notice I didn't even bother asking what the acceleration is because it doesn't matter. It just is an object. It could be a tennis ball. It could be a bowling ball. It could be a penny. If we're ignoring air resistance, the acceleration for all objects will be negative 10 meters per second squared. So we know the delta y, that's given to us. The displacement is negative 20 meters. Now, the initial velocity is known also, a drop projectile. If an object is just dropped, just released without any force pushing it down, the initial velocity is going to be zero. So let's take that third problem solving step and look for the equation that has these four variables. It's going to be that second one. So now I plug everything in. Now notice how, because my initial velocity is zero, well, I don't have to worry about that first term. So I plug everything in and I just solve for the unknown, that delta t, the time interval, and I'm going to get 2 seconds. Now notice I put 2.00 seconds. I have to take into account those significant figures. So now I can solve for the velocity. Well, if it hits the ground, falls from a height of 20 meters, what velocity does it hit the ground? Well, we can use any three of these equations. And if you use the bottom equation, even if you calculated the time wrong, you'll still be able to get the final velocity. But I'm just going to use the top equation just because it's easier, right? So just because now I can calculate the final velocity, and it's going to be negative 20 meters per second. That means that it's moving down at 20 meters per second. So now here's another question that we can ask. A known velocity problem. So an object lands on the ground with a velocity of negative 50 meters per second. What is the time interval of this fall? What was the displacement of the object? Okay, let's ask ourselves those questions. What's the first thing it's asking us to find? It's asking us to find that time interval, the delta t. So what three things do I know? And notice that if we're ignoring air resistance, the acceleration for all objects is going to be negative 10 meters per second squared. Well, I know the final velocity is negative 50, and I know the initial velocity because it was dropped like at it starts at rest. So I know these three variables. So now I have to look for the equation that has these four variables. It's going to be that first one. So now I can just plug everything in and I solve for the time interval, and it's going to be 5 seconds. So it fell for 5 seconds. Now I can solve for the displacement, that delta y. So I can solve for the delta y. I can use any three of these equations. I'm just going to use the second one because it's easier. If I messed up with solving for the time, then yes, I will mess up the delta y. But you can use the fourth equation if you're unsure about this. But I'm going to use the second one just because it's easier, right? So I'll plug everything that I know in, and I know it's going to fall from a height of negative 125 meters. So now the last question is going to be a known time. So now an object is in free fall for 10 seconds. What was the displacement of the object? What was the velocity at the end of the time interval? So here's my delta y, right? So I'm looking for the displacement. What height did it fall from, right? So what height? How far did it fall? So I know the time interval that's given to us, 10.00 seconds. Notice that's four significant figures now. And once again, I know the initial velocity. It's going to be 0. So now I look for the equation that has these four equations. It's that second one. I plug everything that I know into it, and it's easy to solve. Now my displacement, well, it fell negative 500 meters. Notice it's four significant figures. So now I can solve for the final velocity. If it falls for 10 seconds, well, what velocities are going to hit the ground? Or at the end of the time interval, what will that be? I can use any of these equations, but if you want to make sure you're right, even though if you calculated the displacement wrong, that fourth equation will be the one used. But I'm going to use the first one just because it's easier, right? And I'm going to get negative 100 meters per second. All right, so now that we know how to do a couple of these problems, let's answer this question. How can the kinematic equations be used to calculate reaction time? So we did the ruler drop lab. Well, what we did was we dropped a ruler and somebody was trying to catch it. So one person drops a ruler, the other tries to catch it, and we can use that distance that they caught it with to calculate the reaction time. Now, the first thing you need to do is we need to look at the ruler and we need to figure out how are we going to record this data. So the ruler is used to measure length. What's the resolution of the ruler? So we're going to be using the metric side. So if we look at the centimeters, notice that well, the resolution is going to be those individual dash marks. So each one of those dash marks is 0.1 centimeters or 1 millimeter or 0.001 meters. And it does have an uncertainty digit. If it falls in between those two, in between two of those, you can make an estimate to the next digit. So if we look at this one, right? So like if you look at this one, the first scenario was dropped without warning, and you notice those numbers there. Notice I did, even though I fell, it fell directly on the 25, directly on the 27. I still have to record the resolution and that uncertainty digit. So then, in order to, I have to convert it to meters. So all I have to do is move the decimal to the left 2 times, and I like if it's at 25 centimeters, well, the ruler catch that's going to be 0.2500 meters. So now we can calculate the math. Now we can calculate that reaction time. So let's look at the ruler drop math. So a ruler is dropped and falls down for a displacement of negative 0.2500 meters. Notice we had to make it negative because it's falling down. The final position is below the initial position. So what is the time interval of this fall? So I know the acceleration. It's falling during that. It's accelerating at negative 10 meters per second squared during that time. I know the initial. I'm looking for the time, the reaction time. I know the initial velocity was 0. The instant that person let that ruler go, the initial velocity was 0. So now I know the displacement. That's what we were measuring with this lab. So now I can plug everything that I know, and I can look for the equation that has these four variables. It's going to be the second one. So I plug everything that I know into there, and I'm going to get a reaction time of 0.2236 seconds. Notice that it's four significant figures, right? The least amount in my problem. So that's the reaction time. That's how much time it took that person to process that the ruler was falling and send a signal down their arm and close their hand. That's the reaction time. So here's the question. A person walks up to you on the street with $100 bill and says that he will drop the bill through your hands without warning. And if you catch it, he will give you $100 bill. But if you miss, you have to give him $5. Do you accept the challenge? Why or why not? And the hint is the length of a $100 bill is 15.6 centimeters. So if you look already just at the data, the ruler catch, like, really fast reaction time. Like notice that the ruler catch was 25 centimeters, so 10 centimeters apart. Now, if we just look at the graph, well, notice that to catch a dollar bill or that $100 bill, it'll go through your hands in 0.175 seconds. That has to be the reaction time. If you start at one end and just barely caught the other end, that would have to be the minimum reaction time that you would have. Now, the average human's reaction time is 0.2500 seconds. So unless the person accidentally closes their hand as the bill is falling, it's not possible to catch that $100 bill. So there are different apps and websites that you can do to calculate your reaction time, and you'll see that you're not going to be fast enough because people don't have reaction time of 0.1750 seconds. Even like the fastest, Formula One drivers or pilots don't have a reaction time of that. So let's ask this original question. Well, how is a drop projectile represented graphically? So we've used these graphs before. When graphing an object's position versus time, the slope of the line is velocity. When graphing an object's velocity versus time, the slope of the line is acceleration. So now let's look at graphing projectiles. So the object, when you're dropping it, starts at the origin, at that point 0. Now we know that it never goes above the origin as it's falling down. So my graph isn't going to be anywhere above that origin. It's only going to be on the bottom part of this graph. Now the slope of this graph represents the slope of a position versus time graph is going to be the velocity. And we know that objects don't fall at a constant velocity, they're accelerating. So that means it's going to look like this. Now notice the slope of the line changes at every point, just like the velocity changes at every point. So now let's look at the velocity versus time graph. So the instant this person lets go of that object, well, it's at rest. If we look back at the other graph, the initial slope, that instant slope was going to be 0. So it starts at rest. And at no point is that object going to be moving upward in the positive direction. So my entire graph is going to be on the negative side. Now, the slope of a velocity versus time graph represents the acceleration. So the slope is going to be a straight line because it's a constant acceleration of negative 10 meters per second squared. This is what my graph is going to look like because it starts at 0. And notice that it gets faster as it goes down, but the slope is constant because the slope of that line is going to be the acceleration. And if I graph acceleration versus time, it's going to look like this. So in order to look at this, we did the drop projectile simulation. And when you drop a projectile, if you look at the graph off the right, that's what it looks like. Now in this one, they put the origin where it landed, but it's fine because notice that the graphs look the same. So the slope of that top line, when it does the position versus time, we'll notice that the slope of that line is going to be the velocity. And notice that when you're graphing the velocity, that like lime green one, well, it starts at 0 and then it goes negative, and the slope of that line will be the acceleration. Notice the acceleration doesn't change. However, if you look at the bottom graph, notice it does change if you add an atmosphere. So the acceleration slowly goes to 0. Now, if we look at the directions of the velocity and the acceleration of the projectile falls, both the velocity and the acceleration are negative, and you can see that on the graph. Now, what does that mean? So if we look at this, notice that if an object is speeding up, the acceleration will be in the same direction as the velocity. So if we look at that falling object, the velocity and the acceleration are in the same direction, which means it's speeding up. So yeah, it's getting faster and faster as it's falling. So now let's look at another question. Will dropping a penny off the Empire State Building kill someone? So this is just a myth. Now, obviously, don't do this, and if you go up to the observation deck, they don't let you test this out. But the Empire State Building. So a penny is dropped from the observation deck of the Empire State Building and falls for a displacement of negative 380 meters. What is the time interval of this fall? With what velocity does it hit the ground? So let's just find out the time interval. So that's what it's asking us to find. And we know these three things. If the instant you let go of that penny, the initial velocity is going to be 0. We know the displacement. You can just look up the observation deck negative 380 meters. So it's falling 380 meters down. So now I need to look for the equation that has these four variables. It's going to be this one. So now all I have to do is solve for the unknown, which is that delta t, the time interval. So it would take 8.7 seconds to hit the ground. Now we can calculate the velocity that it hits the ground at. Well, I can look at all of these, and I could use that fourth one just in case I calculated the time wrong, but I'm going to use the first one just because it's easier. So it's going to hit the ground with negative 87 meters per second. Now, what does this all mean? Now, that's not enough to kill somebody. It'll sting somebody, but obviously, disclaimer, don't do this. But it's not, and it's because, well, there is some air resistance, right? So that brings us to terminal velocity. Terminal velocity is when the air frictional forces balance gravitational forces. Two objects of different mass only fall at the same rate in a vacuum. In the atmosphere, drag forces act on the object as it moves through the air, or that fluid. So notice that the magnitude of the acceleration goes to zero as the drag increases. The velocity goes to a constant velocity. That's what terminal velocity is. It's when the air forces balance out the gravitational force. So you notice that the faster you go, the more air. If you just move your hand back and forth, you'll feel some air resistance. But if you're driving in a car and you stick your hand out, you're going to feel more of a force the faster you're going. And eventually, if you're in free fall, that air will balance it out. So let's look at this question though. This one's kind of a tricky one. From what height would you have to drop an ant in order to kill it? Well, if we look at terminal velocity of different objects, a human, well, terminal velocity about 134 miles per hour. Now it goes down, raindrop, terminal velocity of 20 miles per hour. Now the terminal velocity of an ant is about 3.9 miles per hour. That's not enough to kill an ant. Ants can survive falls from any height. It doesn't matter whether you drop an ant from 4 feet, it's going to reach terminal velocity, just sort of land. If you drop it from 30,000 feet out of a plane, it's going to reach terminal velocity very quickly, and it'll take a while to get to the ground, but eventually it'll just land on the ground. So, you can read that link for more information. Ants don't fear gravity. It doesn't harm them. So now let's answer this question. Now that we talked about terminal velocity, how did Felix Baumgartner set the world record for the fastest person in free fall if he was limited by terminal velocity? So let's look at Felix Baumgartner's jump. On October 14, 2012, Felix Baumgartner set the world record for the highest free fall and highest manned balloon flight. The balloon he piloted climbed to the stratosphere to a height of 39,045 meters. So that's about 24 miles up. He pulled his parachute cord 1,500 meters above the ground. Once he pulled his parachute cord, he started traveling at a constant velocity. From the time he jumped to the moment he landed on the ground was 9 minutes and 2 seconds. That's 542 seconds. Answer the following questions. So let's look at Felix Baumgartner's jump. Now, the air thins the farther you get above sea level. So if you ever travel to like Denver or somewhere at a higher altitude, you notice that it's harder because the air is thinner. Now, at the height of 24 miles, which Felix Baumgartner jumped from, there is barely an atmosphere, like barely. There is a little bit, right? But not really a lot. And you can see on that graph, it doesn't even go up to 24 miles. It's barely, just like, just in the low percentages of it. Now, so when he jumped, you can see here that he was able to accelerate faster and faster because he didn't have that much of an air to slow him down. So his terminal velocity was changing, but there was barely a terminal velocity at the top because there's barely an atmosphere. So during the stratospheric dive, Felix reached the top speed of 843.6 miles per hour. Now, to put that in perspective, the speed of sound, like just on air, is like close to 700. I think it's 767. It varies depending on temperature and altitude, but he was falling faster than like what we consider the speed of sound because the air was so thin. It limited his terminal velocity, or it stopped. So let's look at free fall. So Felix started at a height of 39,045 meters, and he's accelerating until he pulls his parachute cord above the ground at 1,500 meters. So calculate the time he was in free fall, then calculate his velocity as he pulled the ripcord. So notice that, I'm going to have a delta t here. I'm looking for the time interval it takes because he was just in free fall, because at that we can ignore the atmosphere. So I know the height. Now notice that I had to do a little subtraction here. 39,045 minus 1,500 is 37,545 meters. That's how far he was in free fall. Now I can solve the time with that second equation, and I just plug the numbers in there, and I'm going to get 86.65 seconds. That's how far he was in free fall. All right, so now I can look at that final velocity. So what velocity did he pull that ripcord? Well, I'm going to use that first equation, and I'm going to get negative 866.5 meters per second. Now, let's look at that. So now he's traveling at a constant velocity. Now, the total time Felix was in the air was 9 minutes and 2 seconds, 542 seconds. So Felix pulled the ripcord 86.65. That's what we did. We just calculated that back in the free fall part. Later, at 1,500 meters above the ground, which caused him to travel at a constant velocity. What was acceleration at the time of traveling at a constant velocity? Well, the acceleration is zero if you're traveling at a constant velocity. And what velocity did he land on the ground? So we know the acceleration is zero. We know the time interval. We can do a little bit of math. It's 542 minus the 86.65, and we know he's traveling down 1,500 meters. So I'm going to use that first equation to solve, and here's why. Because well, first I know that the final velocity is the initial velocity, right? So that's what that means. So now I can solve. If I solve for the initial velocity or final velocity, it doesn't matter. But I'm going to use that first equation. The final velocity will be the initial velocity because he's not accelerating. So now I can use this equation. I can calculate that initial velocity. So he's going to land with the same velocity that he does, and it's negative 3.3 meters per second safely on the ground. So if we graph this drop, notice that, well, he's in free fall for a while, and then he travels at a constant velocity. So the slope of this line, he's in free fall, he's accelerating, and then the slope of that line, eventually he travels at a constant velocity. Now, if we look at the velocity, yeah, he's in free fall for a while, but then eventually he pulls the parachute and then he starts traveling at a constant velocity downward. Now, this is the tricky part because if you look at the slope, notice the slope of the line is initially zero, but as it's going upward, there is a positive slope there. So he's going to have a positive acceleration when he slows down, and then eventually it's going to be he's going to level off and have an acceleration of zero. So these are the graphs, the actual graphs of him. Now notice that some of the numbers had to be like fudged a little bit just because, yeah, as he was going down, it was sort of a exponential, like he was adding more air, so it constantly changed. You can see here that his actual speed, well, he was in free fall. He just kept accelerating until he reached until about 50 seconds later, right? So about 50 seconds later, he hit enough of the atmosphere to sort of slow him down. So just remember, as a final thought, there's too much unknown in the universe to take a break from learning. Get out there and question everything.